From the following list of aqueous solutions in water, select the one with the highest boiling point. First thing we need to do is ask what that really means. That means the most particles in solution, because sometimes it might say highest freezing point, or it could say lowest boiling point. You want to make sure you get that straightened away. We're going to think about it in the same way. Potassium nitrate going into solution, we get these ions, and I see 2 for every 1. So this is really like 2 molar in particles. Let's just go down the line. Sodium chloride. So I still have the 1 to 2, and it says I have a 0.75. So my total particles are going to approximate what? Double that. Just like up here, I really doubled my 1 molar there. All right, now C says I have, looks like cupric chloride or copper 2 chloride. Copper 2 in solution, 2 chlorides. Look at this, 2 of those, 1 of those. So I get 3 particles for every 1 I put in. And it says I'm at 0.75. So what's that? It's like 2.25. D, now we have a non-electrolyte. I'd want you to look and say, there's no metals, there's no iron, this must be molecular. So I get what I get there. It says 2 molar on the bottle. I might come up with a 1 to 1, doesn't disassociate. Yeah, 1 to 1, so times the 2. So now we should have enough information to figure this out. Which one do you want to select? Yeah, C has the most particles in here. It's going to elevate the boiling point the highest, or we're going to say it's going to lower the vapor pressure, mole fraction. C, right here. That is correct. From the following list of aqueous solutions in water, select the one with the highest freezing point. So we just 1 potassium, 1 nitrate, so this is like 2 molar. Get 2 particles, so double that. That's like 1.5. And this would be our 2, looks like almost the same question. Is the lowest, least amount of particles. It's going to have the highest freezing point. An aqueous solution of a soluble compound, a non-electrolyte, prepared by dissolving 33.2 grams of the compound in sufficient water to form a 250 milliliter solution. The solution has an osmotic pressure of 1.2 atmospheres at 25 degrees Celsius. What is the molar mass of the compound? Osmotic pressure is equal to number of moles per volume, that looks like molarity, times RT. So this was what was in the slideshow. Since we're in atmospheres, the value of R we probably want is this one that looks like liters, mole, Kelvin. One other little point of business, we want to be in Kelvin. That look uppercase. So now we got everything we kind of need, but I'm thinking we could probably rearrange this. I'm going to divide both sides by RT over there, and then multiply both sides by volume. So let's plug everything in. I got my 1.2 atmospheres of osmotic pressure, my R value point, and then my Kelvin temperature, 298.15 Kelvin. Let's see what this looks like. Kelvin goes away there. Oh, I need to multiply by volume still. So I'm going to turn that into liters. That'd be another thing we'd probably want to do before we got started. Go 250 mils, 1,000 mils per 1 liter. Liters, atmosphere. 1 unit remains. So it's always good to, before you do any calculation, make sure all your units are right. I'll tell you whether your algebra is right. 0.25 times 1.2 divide 0.0821. Divide 298.15, hit enter. I got the whole thing there in my calculator. So there's our moles. What is the molar mass? That's the units grams per mole, right? That's molar mass. I'm going to look up here. I'm going to grab my 33.2 grams divided by this many moles. So I'm going to go 33.2 divided by my answer there. There's my answer. That's possibly only 2 digits. And the atmospheres is only 2. Yeah, most of the time if I think the book's wrong, I'm wrong. Exciting new chapter on kinetics, chemical kinetics. What is that? Kinetics may be concerned with the speeds or rates of chemical reactions. Some reactions are very slow, like geological time scale. Others are very fast, like high explosives. What do we learn from chemical kinetics? How long a medicine can work? Fancy word for that would be pharmacokinetics. Here's an environmental question. Ozone depletion, reaction mechanisms. We know the kinetics of a reaction. We can stipulate a very plausible reaction mechanism. So what factors affect reaction rates? So the physical state of the reactants. Talked about things reacting on a geological time scale. Solids typically react kind of slow because we kind of have this collision model that says in order for molecule A to react with molecule B, they got to come in contact with each other. Solids sometimes having a hard time moving around and becoming in contact with each other. But gases can react very fast, explosively. Think about the combustion in your car engine. That happens real quick, especially if you've got your Kawasaki Ninja revved up to like 15,000 RPMs. Man, that's a lot of combustion reactions occurring. So back to this collision model, the more concentrated things are, or at higher pressure, if we want to go back to a car engine, better compression, better combustion, temperature at which the reaction occurs. I always ask my students, why do you have a refrigerator at home? You say, well, I don't want my milk to spoil. How's a refrigerator stop your milk from spoiling? If you leave that milk long enough in the fridge after you open it, it's going to spoil. So higher temperatures, things move around with more kinetic energy. More kinetic energy, they can run into each other more often, and when they do run into each other, they have higher probability of a reaction occurring because they have more force when they run into each other. And then lastly, a presence of a catalyst. Anybody know the definition of a catalyst?
Isn't it something that speeds up a reaction?
Yeah, that's about half of it. Not actually, that's more like 3/4 of it. It speeds up of a reaction and is not consumed in the reaction. So it's typically unchanged. Physical state of the reactants. In order to react, molecules must come in contact with each other. The more homogeneous the mixture, that's going to occur. So typically I like to pull out a lighter and a nail and try and light it on fire and ask you whether still is combustible. Big nail, my lighter. Right. So the physical state of the reactants. So here's a piece of steel wool. You can kind of light it on fire and it'll burn a little bit. Here they've stuck the steel wool into oxygen-rich atmosphere. Temperature. So going back to your fridge, if you leave your milk sit out at room temperature, those microorganisms have a bigger appetite. They're more alert. They move around quicker. Everything moves at a quicker rate. Reactant molecules have more kinetic energy. They move faster, collide more often, and with greater energy. So a lot of reactions in the lab, you got to heat them. Give things enough kinetic energy to react. Presence of a catalyst. Catalysts speed up reactions by changing the mechanism of the reaction. Towards the end of the chapter, we'll see that it lowers the energy of activation, and catalysts are not consumed during the course of the reaction. So we mentioned kinetics has to do with the speed of a reaction. 75 what? Presumably miles per hour. So a reaction is no different where we're going to have some change that occurs per time. And so we can measure concentration normally, and we can look at either reactant disappearing or a product forming with time. We've set it up so it's independent of that. So the speed of a chemical reaction is its reaction rate. Here's a nice organic reaction. Something like tetrabutyl chloride. You plop it down in water, you're going to make tetrabutyl alcohol and HCl. So we can imagine a liter of solution, and we take 1/10 of a mole of this stuff, and we plop it in there and mix it up. So at time 0, we have 1/10 of a mole of this reactant. I said liter, so it's 10th molar. It's always nice when your volume's a liter, then molarity in moles is the same. 50 seconds later, we measure the concentration of our tetrabutyl chloride, and instead of 0.1, we see 0.0905. 100 seconds later, we got less, and you can see the concentration of our reactant is dropping. And so over here we have the rate defined as minus the change in the concentration of our reactant per time, or it could be just the change of our product per time. We put that negative sign there, and then these two things are equal. So it doesn't matter whether we look at product or reactant. But here was our time, 0.01. Why don't I just put maybe the first three? There's our molarity. And then here we had this thing they called average rate, having the units molarity per second. All right, let's see if we can calculate that rate. We said rate's going to be defined as minus the change in our C4H9Cl per change in time. So I'm going to go here at 50 seconds. I'm going to look up here and say a negative 0.0905 minus 0.1 divided by 50 minus 0. That should equal my rate. 0.0905 minus 0.1. Look at there. There's a negative number. That negative sign is going to get rid of that. 50 minus 0, that's 50 seconds later. Divide 50, and then times by a negative 1. That's what it's out there. There's where we get the 1.9 times 10 to the negative 4th. So we counted the rate there and the rate there. And what do you notice is going to happen to the rate? What?
It slows down.
It slows down. So what have you learned this morning that would explain to you why it slows down?
Because there's less of the stuff.
Right. This idea that concentration affects rate as the reaction cruises along. You're burning up reactants, and there's less and less reactants, so all reactions tend to slow down.
So if you were to add in more reactant, would there be a jump back up a little bit? And then
rate? Yep. Absolutely. And so a lot of chemical enterprises, that's how they run their reactions. They're constantly adding reactant and removing product. And you'll see that's an equilibrium thing that we'll deal with
eventually
in chapter 15. And then how many of you like calculus? How many of you have done calculus or in calculus? Yeah, so right here you see maybe calculus in action. Here's what I remember. When you find a derivative of some function, you find the slope of the line tangent. And so here is like an instantaneous rate. So now we're going to look next what happens when we don't have one-to-one stoichiometry. Right here it was nice. One reactant, one product. We could write a rate like this. Now here we have two reactants forming one hydrogen, 1I2. We can write a rate expression. I said it doesn't matter if we look at reactant or product. So here our reactant is changing twice as fast as products are forming. So we divide by this 1/2 to make it all nice and equal.